Hello and welcome to another power electronics class. In the previous class, we started the single phase AC phase control systems. We started with the half wave AC phase controllers, which are unidirectional ones. And we learned in these systems, we usually use one thyristor or SDC, and the system can only control the output in a single half wave of the system. So as you can see, here we only control it in the positive cycle. And the output RMS voltage for this system was Vs square root of 1 over 2 pi minus alpha plus sine of 2 alpha over 2. And we solved the practice problem, by the way, for these systems as well. And we realize in these systems the Vs can oscillate or move between 100% V out. RMS can move between the 100% of Vs and 70%. So therefore, we can't go to 50% or 0, and that's a limitation. Sometimes we need to get lower voltage in the output. Therefore, a half wave phase controller would not work. Today, we're going to continue with AC phase controllers, and we want to continue with full wave AC phase controllers, which usually use a triac or two thyristors SDCs. And we're going to also continue with different loads connected to them. So we would first study the R load and then RL load and so on. Now, let's solve an example for a half wave system. So this example would show the DC voltage of a half wave single phase AC voltage controller. So we want to derive an expression for DC voltage in a single phase AC voltage controller based on the output voltage waveform as shown aside. The VODC can be found as derived below. Now, how can we find the DC voltage? Sorry. We need to derive the area to be able to find DC voltage that we have here. Now, V out DC in this case is going to be 1 over 2 pi because we're going between 0 and 2 pi. Integral of alpha, because between 0 and alpha, we have 0 volts in the output. So it's going to be 0. So we're going to start from this point, and we're going to find all of this. Now, V out DC, if we simplify the Vm sine of omega t, it gives us negative cosine of omega t from alpha to 2 pi. And therefore, VDC is going to be Vm over 2 pi cosine of alpha minus 1. We already know that Vm is square root of 2 Vs because it's a sine wave. And hence, the VDC is going to be square root of 2 Vs over 2 pi times cosine of alpha minus 1. Now, when alpha is varies from 0 to pi, then VDS varies from 0 to negative Vm over pi. So if you just replace alpha with 0, cosine of 0 gives us 1, and 1 minus 1 is 0. 0 times square root of 2 Vs over 2 gives us 0. Again, if this is 0, alpha, this would be 1. 1 minus 1, this would be completely 0. And when this is pi, for example, we're going to have negative 1. Negative 1, negative 1 is going to give us minus 2. And minus 2, so again, if this is pi, this is going to be negative 1. Then we would have negative 2 over here. So what we have is going to be square root of 2 Vs over negative pi, and square root of 2 Vs is Vm. In other words, this is negative Vm over pi. Now, there are some disadvantages of the single-phase half-wave AC voltage controller. The first thing is this exact example. We're going to have a DC component, and this DC component, since we are in an AC system, most likely if this is connected to an induction motor or a transformer, it's going to saturate the core. In a transformer, we do not want to have a DC current going inside a transformer. Why? Because if you put a DC current inside a transformer, the core becomes like a permanent magnet, and it's going to saturate the magnetic of the core, and therefore it's going to create some problems, reduce efficiency, create extra heat, etc. So the DC component, we don't want to have it. It's a problem. Second thing is obvious from this graph we see here. The problem is that we can only control the AC voltage in a single half. We have no control of it in the negative cycle. We can only control it, for example, in the positive cycle. So we're limited on how much control. So the maximum that we can do, as mentioned, is like 70%, and we don't have any control in one cycle. We just have control in half of the cycles. And the final problem that we have is that we have limited control over the RMS voltage. As you saw here, we can only change the RMS output between 100% and 70%. So we can control it between 70.7% to 100%. So if in the exam question comes that what are the limitations or disadvantages of half-wave single-phase AC voltage controllers, and the problems are, first, because of the DC component, it's going to saturate the core if we have a induction load like a transformer or a motor. Second thing is we only have control over half a cycle of the power, AC power flow. And the third problem is that we have limited power over the RMS output voltage. We can only alternate between 70 and 100%. Now, what is the solution to these problems? We can use a single-phase full-wave AC voltage controller. Now, for this, instead of having one SCRs, we're going to have thyristors or triac. We can use two SCRs or two thyristors or a triac. So we can have one for each cycle. In the previous one, we only had one SCRs or thyristors. Let me see if I can. Only we had one of them. Now in a full wave, we have two of these. Or we can have a triac as well. So we can have a back-to-back SCR or silicon-controlled rectifier, or instead a triac can be used for bidirectional full-wave AC choppers. Again, we can use thyristors as well. So the thing with thyristors, we have control on the fire angle, but when it gets into reverse, it automatically shuts out. So the SCRs work like that. We have control on when it fires or alpha, but when it gets into reverse bias, it automatically shuts off. Now, the main waveform for this full wave system for omega t is equal to alpha to pi, and omega t equal to pi plus alpha to 2 pi. V out would be equal to VL, would be equal to Vm sine of omega t. So now for the previous one, we saw that we only had control on half of the cycle, and the output looked like this for the voltage. But here we have control over both the positive and the negative. By the way, the upper one is the voltage. I'm going to draw it with blue. And the lower one is the current. I should with green. So voltage, blue, and current. Now, as you can see, we have control on both the positive cycle and the negative cycle. And we would assume that here we only have a resistive load, by the way. This is with a resistive load. And when we have a resistive load, we won't have, and by the way, I mentioned here as well, it's with a resistive load only. And when we have a resistive load, we won't have any shift in the phases between the voltage and current. So they have the same phase, they are synchronized. But the current here is going to be just V out over RL, which is our resistance. If we had an RL load, then it would be a complete different story. It's going to be a little bit more complex than just a single resistive load. Now, I out here is going to be Vm sine of omega t over RL. In other words, it's going to be Im sine of omega t. So that's the reason the current has a lower magnitude than the voltage. Now, the RMS output voltage, V square of L RMS, is going to be 1 over 2 pi, the integral of alpha to pi, Vm sine of omega t squared, d omega t plus P plus alpha, which is the negative cycle, to 2 pi, Vm sine of omega t squared d omega t. And after simplification, VL RMS is going to be Vs times square root of 1 over pi minus alpha plus sine of 2 alpha over 2. Now, this equation may look very similar to the previous one. The only difference between the half wave and the full wave, if you want to memorize or learn this equation, is in half wave, this part was 2 pi minus alpha over and 1 over 2 pi. So if I go back to that equation, you can see it's 1 over 2 pi and 2 pi minus alpha. Here, we just find it in each cycle, so it's 1 over pi times pi minus alpha plus sine of 2 alpha. Now, for this, let's put alpha equal to 0. What happens if alpha is equal to 0 to the VL RMS? And by the way, we would assume we don't have any loss in the system. So alpha equal to 0 means we start from 0. So we don't cut anything from the input. Therefore, VL would be equal to what? Let's solve this. This is 0 and this is 0. Sine of 0 is equal to what? 0. So this would be 0. And pi minus 0 is 0. So 0. Pi times 1 is going to be pi. Pi over pi is equal to what? 1. So VL would be equal to Vs square root of 1. In other words, VL would be equal to Vs. And it's obvious, if I start from 0, VL and Vs would be equal. Okay? So if I put alpha equal to 0, then the maximum voltage appears across the load at alpha equal to 0 again. And in that case, VL would be equal to Vs. Now, where would minimal output appear? If alpha is pi or 2 pi, which one? So if we put alpha equal to pi, then pi minus alpha is pi minus pi is going to give us 0. Am I correct? And what is the sine of 2 pi? Zero. So it's going to be 0 times 1 over pi gives us 0. Vs times square root of 0, which is 0, gives us 0. Okay. So if we have pi, obviously you can see that we start from pi, this point, you're going to have nothing left from the signal. Okay. So now we realize that the maximum is oscillating between Vs of the output and what? And 0. Okay. Now, as mentioned before, VL RMS, if alpha is equal to 0, is going to be Vm over square root of 2 or Vs, as we shown before. And you can see the benefit of this system is that the output RMS oscillates between Vs and what? Vs and what? And 0. For a half wave, it would alternate between what? 100% and 70% of Vs. But here, it goes all the way down to 0%. So we have better control. We don't have the DC problem. We have a little bit of that, but mostly we don't have any problem with being able to precisely control and have a wide range of control over the output. So a typical control characteristic of a signal phase, full wave phase controlled AC voltage controller is as shown here. We can notice from the figure that we get a full range output voltage control by using a single phase full wave AC voltage controller. Now in these systems, usually to be able to control each of the SCRs, and by the way, these are the gates for the SCRs, we need to usually oscillate them, because if we don't oscillate them, it's going to create some problems when we trigger them. So in the full wave single phase AC voltage controller circuit using two SCRs in parallel, the gating circuit or the gate trigger pulse generating circuit of thyristors must be oscillated. And this figure shows a pulse transformer with two separate windings to provide isolation between gating signals. And by the way, we want these signals to be able to synchronize them. So when one turns off, the other one immediately turns. But we want to have control over them as well. Now, to calculate the output RMS current, the output RMS voltage, and the output voltage and also the output power, again, we use the equations to find the area under the curve. And for the RMS output voltage, as mentioned, it's going to be for its maximum when alpha is 0, V out RMS is going to be Vs, or the RMS input supply voltage. I out RMS is going to be V out RMS over RL, which is the RMS value of the load current. IS is going to be I equal to I out RMS, or RMS value of input supply current. And the output load power here, P out is going to be I square output RMS times RL. Now, if we want to find the power factor, the input power factor would be equal to P out. Again, we don't have any loss here. We have a resistive load, so we don't have any shift in the phase. We can find PF. It's going to be the same as the input and the output are going to be the same. So PF is going to be P out over Vs IS, and therefore it's going to be I out RMS times RL over Vs. Power factor is going to be V out RMS over Vs, which would be equal to, from the previous equation that we had, it's going to be square root of 1 over pi minus alpha plus sine of 2 alpha over 2. Now let me give you an example. I want you to find the power factor when alpha is equal to 45 degrees, and alpha is equal to 15 degrees. So we want to find the power factor when alpha is 45 degrees and alpha is 15 degrees. By the way, again, in your exam, I will provide all the equations. You don't need to memorize them, but try to help multiple examples so you get familiar with the equations and everything else. Okay, did you solve it? Or you need more time? Good. Tyler, did you solve it? So power factor for alpha equal to 45 degrees is point. Perfect. And what about the second one? What do you have? Yeah. So it should be less than that, probably 0.9 or something. Okay. Now, I'm going to give you this as an exercise to solve it at home, and I'll give you the results next week. It's going to be pretty straightforward. Now, to find the average thyristor current, again, we will find the area because we want to find the average current under the curve. And for that, IT average is going to be 1 over 2 pi alpha to pi IT d omega t. And when we simplify that, we get to this equation. IT is going to be equal to IT average, or the thyristor current average, is going to be Im over 2 pi 1 plus cosine of alpha. And the maximum average thyristor current for alpha equal to 0 is going to be equal to Im over pi. And the RMS thyristor current would be equal to the same equation that we had for the voltage times Im over square root of 2. So the second part is the same that we had for the RMS voltage, because the shape of the graphs are exactly the same and they don't have any phase shift. And the maximum RMS thyristor current for alpha equal to 0 is going to be equal to Im over 2. Now, note that in the case of a single phase full wave AC voltage controller circuit using a triac with the other part, resistive load, the average thyristor current should be equal to 0 because the triac conducts in both the half cycles and the thyristor current is alternating, and we obtain a symmetrical thyristor current waveform, which gives an average value of 0 on integration. Again, the reason that we only calculated this in the positive side because each thyristor in this case is only conducting in one half cycle. So this one is going to be in the positive cycle, for example, and the other one I'm going to draw it with blue is going to conduct in the negative cycle. But the triac, because it does in both positive and negative, they're going to both cancel each other out because it's a symmetrical. Therefore, the average voltage, current, is going to be equal to 0 for a triac. But for each thyristor, because it's half of that, it's going to be equal to this equation that we had here. Now let's find the average current for a thyristor at alpha equal to 45 degrees. And also alpha equal to 90 degrees. Oh, and by the way, Im is, let's say, 5 amps. So the first one is going to be 5 over 2 pi, 1 plus cosine of 45 degrees. Cosine of 45 degrees is 0.7. Am I correct? Double check it. So it's going to be 1.7 times 5. It's going to be 8.7 divided by 2 pi. It's going to be 1.35. Did you get the same thing? It's going to be 1.35. So the first one, it's going to be 1.35. And what about the second one? Cosine of 90 degrees is what? And so it's going to be 1 plus 0. It's going to be Im over 2 pi. 5 over 2 pi is going to be what? 0.78. Going to be 5 divided by 0.78. And obviously, if alpha is equal to 0, it's going to be double that. So it's going to be Im over pi, which is around 1.56. So the average maximum is 1.56. Oh. Let's do a small quiz. I think it's, again, mainly for attendance. But you're going to have at least one question from this on your next exam. So, oh, by the way, your next exam is going to be next Wednesday. On Monday, we're going to have a review session. And on Wednesday, we're going to have our second exam. So, question is this. For an resistive load, single phase full wave AC controller, find V out RMS. We want to find V out RMS, I out RMS, and P out. Also IT RMS and IT average. VS is 400 volts. Frequency is 60 hertz. IM is equal to 10 amps. And the firing angle alpha is equal to 30 degrees. So we want to find V out RMS, I out RMS, P out, the I of thyristor RMS and I of thyristor average. For alpha equal to 0, for alpha equal to 30 degrees, VS is 400, F is 60 hertz, and IM is 10 amps. I'm going to go back to the equations. These are the equations that you may need VL or V out RMS is going to be this. And the output power, V out, P out is going to be I square RMS times RL. And the rest of the equations are here. By the way, if you need R is 40 ohms. The resistive load is 40 ohms if you need it. You may need the frequency, you may not need it. I will post another set of homework this week, and you're gonna have 2 weeks after but I would highly recommend that you solve them because some of your exam questions would be from those homeworks. Do you need more time or? Do you need more time or? Okay, I'll give you. Oh, and I forgot to mention, and the power factor as well. We already have, I think the equation for power factor, it's up here. Yes, yeah, it's a great idea, yes. Alpha. Why are you getting a negative? Yes. So, oh, you have to change that into 80. Yes, yes. So, yes, it's 180 and that's a 30 degree. Yeah. Mm. The alpha is in terms of radians, so you have to so much. Again, mainly this is for attendance, okay? Yes, sure. Just VO over VS. Yeah. Thank you so much. Thank you. So I don't think we have enough time to finish the RL load system. I'm just going to give you a brief introduction of that, and we continue that after our exam. So for our situation, the phase of the current and voltage were the same phase. We didn't have any shift in the phase, but when you add an inductor to the load, then the inductor would act like a current storage system. It stores power in it, and therefore it shifts the current a little bit, and you're going to have a shifted load. So in this particular case, if you want to find the power would be the area under this, which is a lower power compared when you have a load. So this is, again, out of our control. Usually we don't have any control of the load, but you could see that same system, the same full wave system connected to different loads, you're going to have different outputs, different voltage, different current, different power outputs as well. And I'll explain this again, as I mentioned. I would explain it after our exam. Our exam is going to be next week. We're going to have a review session before the exam. Exam is going to be the same format that we had in our previous exams. And again, multiple choice questions. I would post an announcement for online students as well. And if you have any questions in the meantime, just please email me. Thank you so much, and I'll see you next week.